like to have our next speaker, Professor Debajit Kalita from Pittsburgh University, and he'll be talking on inverses of unicyclic three-colored diagrams. So I would just like to point out that this digraph, colored tree digraph, has nothing to do with coloration of the vertices of a graph. It is something to do with the edges where they put some weights and things like that. So I would like Professor Kalita to proceed with the talk. Thank you.
Hello everyone. So first of all, I must thank the organizers for giving me the opportunity to talk in this virtual conference. It is a pleasure to be here. So my talk will be on the title Inverses of Unicyclic Three-Colored Diagrams. This talk is based on a joint work with my PhD student, Mr. Kuldeep Sharma. So I acknowledge his contribution. So I begin with the definition of adjacency matrix of a graph. Given a graph G of order n, the adjacency matrix is a matrix n by n matrix, and its ij entry aij is 1 if I and j are adjacent. An example of a graph and its adjacency matrix. And we see that that is singular. Then next we take another graph whose adjacency matrix is this, and we see that this is non-singular. So that means we have graphs where the adjacency matrix is singular, and we have graphs where the adjacency matrices are non-singular. So this is where we give the definition of a singular graph. A graph G is called singular if its adjacency matrix is singular. Otherwise, it is called non-singular. So before moving, we give some preliminary definitions which will be required. So a spanning subgraph H of a graph G is called a spanning linear subgraph if each of the components of H is either an edge or a cycle. And a perfect matching is nothing but a spanning linear subgraph whose components are edges only. For example, we take this graph. This is a perfect matching. In fact, this is a spanning linear subgraph also with a component. So this is a perfect matching for that graph. Fine. Now, we talk about the determinant of the adjacency matrix. The determinant of the adjacency matrix was obtained independently by Harare in 1962 and Sachs in 1964. And they have found this formula for the determinant of the graph, which is very popular and well known. And it is coming in terms of the graph structure. So since we have a non-singular graph, and the non-singular graphs are those graphs whose adjacency matrices are non-singular. So, and we know that non-singular matrices are invertible. And because of that, Harare and Ming, they have defined an invertible graph. And they call a non-singular graph invertible if the inverse of the adjacency matrix is again a 0-1 matrix, because the adjacency matrix is a 0-1 matrix. So if the inverse is also a 0-1 matrix, then they call those graphs as invertible graphs. And with that definition in 1976, they have found that there is only one such collection of, one such class of invertible graphs, and that is namely P2 only. A connected graph G is invertible if and only if the graph is P2 only. So that is a very trivial kind of thing. So that is not much, that is not giving many things. So then, in the year 1985, Goldstill introduced a new notion of inverse. So what he did, so he defined a graph Z to be invertible if S as the inverse S is a non-negative matrix, where S is a signature matrix. Now the signature matrix S is nothing but a diagonal matrix whose diagonal entries are plus minus 1. That is, a graph Z is invertible if the inverse of the adjacency matrix is signature similar to a non-negative matrix, because adjacency matrix is a non-negative matrix. So in view of that, he might have defined this way. And by defining this, and he posed this a problem of characterizing the bipartite graphs with unique perfect matching, which possesses an inverse. So he's posed this problem. And then many researchers worked on that direction, and few of them are listed here. Barik, Neumann, Potti, they have described the inverse of the adjacency matrix of bipartite graphs with unique perfect matching. Then Akbari and Kirkland, they have characterized bipartite unicyclic graphs with unique perfect matching, which possesses an inverse. Then Tiefenbach and Kirkland, they have identified those bipartite unicyclic graphs which have self-inverse. Self-inverse means the inverse graph is isomorphic to the original graph itself. Then recently, Panda supplied several characterizations of bipartite unicyclic graphs with unique perfect matching and possessing bicyclic inverses like that. Now we move on to the direction of weighted directed graph. Now, what is a weighted directed graph? A weighted directed graph is a directed graph whose underlying graph is a simple graph, and each of the directed edges have a complex weight of unit modulus, which are complex numbers of unit modulus. So that type of directed graphs are called weighted directed graph. And by Wij, we mean the weight of an edge directed from I to j. And the adjacency matrix of a weighted directed graph is defined this way. Its ijth entry Aij will be simply Wij, the weight of the edge, if there is an edge directed edge from I to j. Otherwise, if there is an edge directed from j to I, then Aij will be simply Wji bar. And otherwise, if there is no edge in between I and j, then entry is 0. So this is how the adjacency matrix of a weighted directed graph is defined. Then, in particular, what we do, we consider those weighted directed graphs whose edge weights are from this set only, 1, -1, and I. And that type of weighted directed graph is usually known as three-color diagram. This is what three-color diagram. And the edges of weight 1 will be viewed as a red edge. The edges of weight -1 will be viewed as a blue edge, and the edges of weight I as green edges. Just it is how we view, nothing else. It has nothing to do with the coloring of a graph. And then what is the weight of a walk? Suppose there is a walk I to j from the vertex I to j, and then weight of the walk W from I to j is nothing but the product of the entries of the adjacency matrix like this. I1, the I1th entry of the adjacency matrix, then I1, I2, and so on. So this is how weight of a walk is defined. And then in the year 2014, Kalita and Potti, they have given a formula for the adjacency determinant of the adjacency matrix of a three-color diagram, and this is the formula, and it is quite similar to those Harare and Sachs theorem. And this formula, one can view it as a generalization of that Harare and Sachs formula. So this is how determinant of a three-color adjacency matrix of a three-color diagram is obtained. Then we have some notation. By Pij, we mean the ij paths P in the graph G such that either G minus Vp, the Vp is the vertex set of the path P, is empty, or G minus Vp has a spanning linear subgraph H in which no cycle component has weight plus minus I. So Pij is defined like that. And with that, recently we have obtained this formula for the inverse of the adjacency matrix of a three-color diagram. The inverse of a adjacency matrix of a three-color diagram is obtained this way, and this is the formula for that. And then we define the inverse graph for a three-color diagram. So we take a non-singular three-color diagram. That means the adjacency matrix of the three-color digraph is non-singular. That means it is invertible, and say alpha ij is the ij entry of the inverse. Then by G plus, we denote the three-color digraph, not necessarily three-color digraph, the graph on the same vertex set as that of G, constructed this way. Now, two distinct vertices I and J are adjacent in G plus, if and only if alpha ij is non-zero. This is how it is defined. Alpha ij, it is non-zero. And we call G plus the inverse graph of G. Then we move on to the unicyclic case, because what we have seen in the literature that whenever the adjacency matrix of a tree, in general a tree, can be viewed as a matrix similar to the adjacency matrix of a three-color diagram. That means if a graph three-color diagram G has no cycle, then it is nothing but the adjacency up to some similarity. It is nothing but adjacency matrix of a tree. So the study of the adjacency matrix of a three-color diagram, which is basically a tree, is same as the study of the adjacency unweighted undirected tree. So because of that, in this direction of three-color diagram, we try to discuss the unicyclic three-color diagram first. And in the year 2014, this result is obtained. And what it says, suppose Z is a connected unicyclic three-color diagram with a cycle C. Now you see, in a three-color diagram, because weights of the edges are 1, minus 1, I, so weight of a cycle can be 1, minus 1 and I only, or plus minus I. So now we see that if weight of the cycle is 1, then it is the graph Z is I diagonally similar to a unicyclic graph with all edges red. That means a unicyclic graph with all edges red means unicyclic graph where all the edges having weight 1, and which is as good as the usual unicyclic graph, undirected, unweighted unicyclic graph, you can say. Now, I diagonally similar means the adjacency matrix of the graph Z is similar to this unicyclic graph via the matrix S, where S is a diagonal matrix and with entries plus minus 1 or plus minus I. And if weight of the cycle is minus 1, then Z is I diagonally similar to a unicyclic graph with all edges red except one edge on C, which is blue. That means only one edge of the cycle is of weight minus 1 and rest of the edges having weight plus 1. Then if weight of the cycle is plus minus I, then Z is I diagonally similar to a unicyclic graph with all edges red except an edge on the cycle which is green. That means there is only one edge on the cycle whose weight is plus minus I and rest of the edges having weight 1. So this is what was seen in 2014. And in view of this, whenever weight of the cycle is 1, so, and there are many things in the literature, because it is I diagonally similar to a unicyclic graph with I diagonally similar to a unicyclic graph with all edges red, and there are many results. Almost everything is there in case of unicyclic graph with all edges red. So we are not going to discuss those unicyclic three-color diagrams whose weights are 1. Similarly, if the cycle weight is minus 1, then also results are more or less similarly coming as that of the unicyclic graph with all edges red. So what is interesting is this. Whenever weight of the cycle in the unicyclic graph is plus minus I, we are getting very much interesting results. And that is what our target, to discuss about those unicyclic graphs with the cycle weight plus minus I. And we have seen that it can be seen as a corollary to this determinant formula obtained by Kalita and Fati, that if U is a unicyclic three-color digraph with a unique perfect matching, and suppose it has a cycle weight plus minus I, then determinant of the adjacency matrix of the unicyclic graph is simply minus 1 to the power cardinality of M, where M is the unique perfect matching, and cardinality of is just the number of edges in that unique perfect matching. And because of this, now we consider the class of unicyclic. That means this type of unicyclic graphs are non-singular. So, and the determinant is plus minus 1. It can be. So, because of this, we consider the class of unicyclic three-color digraphs with the cycle weight plus minus I and having a unique perfect matching. And this class we will denote it by UG. And now we talk about inverses of such unicyclic three-color digraphs. And this formula gives us the inverse. That means the inverse graph of unicyclic three-color digraph in UG can be obtained by this formula. The adjacency is obtained in this formula. This WP is nothing but weight of the that alternating IJ path. Now, what is an alternating IJ path? Now, alternating IJ path is nothing but an alternating path where the beginning edge is a matching edge and the ending edge of the path is a matching edge, and it is alternately matching, non-matching, matching, non-matching edge. So that type of edges, path is called alternating path. Now the next question is, whenever we have the inverse, so we ask the question, is it true that inverse is also a three-color digraph? So that is what our first question. We take a three-color digraph which is non-singular. We take its inverse. Now the question is this also the inverse also three-color digraph? The answer is no. If we take, for example, this graph, then its inverse is not a three-color digraph. It has some different inverse. So then the question is, when a three-color digraph, unicyclic three-color digraph has a three-color digraph inverse. So we are going to answer that question. Before we answer that question, so we give some definition which will be required for our discussion. So what is a peg? So you take an unicyclic graph, a matching edge which is incident with exactly one vertex of the cycle is called a peg. For example, we consider this unicyclic, and this edge 4, 6, this is a peg, because this is, first of all, this is a matching edge, and only one of its end vertex is on the cycle. This other vertex is outside the cycle. So 4, 6 is a peg, whereas 2, 3 is a matching edge, but 2, 3 is not a peg. Now, this theorem now tells us the unicyclic three-color digraphs in UG whose inverse U plus is denoted as the inverse graph of U, and it is again a three-color digraph if and only if either U is non-bipartite or U has at least 4 pegs. Then U plus is always a three-color digraph. So this theorem characterizes all those unicyclic three-color digraphs in UG whose inverse is again a three-color digraph. Then the bipartiteness. The next question we ask, if the given graph is unicyclic bipartite, whether its inverse is also bipartite? The answer is yes. Okay. So this theorem tells us that if U is bipartite, then U plus is also bipartite, and if U is non-bipartite, then U plus is also non-bipartite. So this theorem tells us the bipartiteness of the inverse. And then we move on to the Laplacian thing. The Laplacian matrix of a three-colored digraph is simply defined dg minus kg, where dg is the degree diagonal matrix. Now, what is the degree of a vertex in a weighted directed graph or three-colored digraph? It is simply the degree in the underlying graph. So, ignoring the direction of the edges, simply that. And we have already in the literature that the Laplacian matrix of a three-colored digraph need not be always singular. Sometimes it can be non-singular. So then we ask the question whether the inverse graph of a unicyclic three-colored digraph can be singular. The answer is no. The inverse graph is always Laplacian non-singular. So given a unicyclic three-colored digraph in UZ, then its inverse is always Laplacian non-singular. And then we are going towards the definition of a simple corona, which will be required for our further discussion. Now, what is a simple corona? A simple corona is a graph which is obtained from another graph G by adding a new vertex of degree 1 to every vertex of G. It is just like this. Suppose G is this graph, then we add edges like this, and the new graph is called a simple corona. Okay. And now, the next interesting question is, we are taking unicyclic graph and we are discussing its inverse. Now the question is it always true that the inverse of a unicyclic three-colored digraph also unicyclic three-colored digraph? We can see in the literature that Akbari and Kirkland, then Barik, Neumann and Potti, they have independently proved that the trees whose inverses are again 3 are nothing but the simple corona trees. That means only simple corona trees are the trees whose inverses are again 3. So that gives us a question to ask whether this kind of thing is true for unicyclic three-colored digraph also. That means we ask the question, does there exist a non-corona unicyclic three-colored digraph in UG whose inverse is again unicyclic? The answer is yes. This is an example, and this is a non-corona unicyclic three-colored digraph whose inverse is again unicyclic. So then we pose the problem of characterizing the non-corona unicyclic three-colored digraphs in UG whose inverses are again unicyclic. And this is how we can construct. So what we do, we take a triangle gamma of weights say plus minus I. Then we take a simple corona tree, which is T is a simple corona tree. Then we identify a quasi-pendant vertex. Quasi-pendant vertex means a vertex which is adjacent to a pendant vertex. And then we join it, attach at the cycle. And the resulting graph is a unicyclic three-colored digraph. And these kind of graphs are non-corona unicyclic graph, three-colored digraphs. And we see that inverse of this unicyclic three-colored digraph is again unicyclic three-colored digraph. And this theorem characterizes all those unicyclic three-colored digraphs in UG whose inverses are again unicyclic three-colored digraph. And these 3 equivalent conditions we get. Okay, U plus is unicyclic if and only if U is a simple corona or U has the structure as constructed above. And whenever we have U plus unicyclic, then we must have U to be isomorphic to U plus. That means inverse graph is isomorphic to the graph itself. That means you can say that they are having self-inverse. One can say that. Now, what is an SR property of a graph? Now, Barik, Neumann, Barik, Potti, and Sharma, they have first introduced this kind of a notion of SR property, and we just take their definition. A three-colored digraph is said to have SR property if it satisfies the following conditions. Now, whenever lambda is an eigenvalue of AG, then 1 by lambda should be an eigenvalue of AG, and the multiplicities of lambda and 1 by lambda should be same. That type of graphs will be called having SR property. And as an application of our results, so whatever discussed here, one can obtain this result, which is obtained by Potti and Kalita in 2014. And that result can be seen via our results found in terms of inverses of unicyclic three-colored digraphs. And what it says, a unicyclic three-colored digraph whose weight of the cycle is plus minus I has the property SR if and only if U is either a simple corona or U has the structure as constructed this way. So either this graph has SR property or a simple corona unicyclic graph has this property. And with this result and application, we conclude my talk, and these are some references. And I thank all of you.
Thanks, Kalita, for the nice talk. So does anyone have a question? Anyone? All right, so there are no questions, that I would like something to Professor Kalita. So
Yes, sir.
yeah, Kalita. So
Yeah.
what you said was that if you have this three-colored graph with I there, and then you need four pendant vertices sort of things, means pegs, four pegs to be inverted.
Yeah.
So what happens for those graphs about the SR property or about inverse being unicyclic or not? What type of graph do you get from there in that case? Have you looked at it, or it is random or something you are not able to make any statements?
Yeah, so far we are not able to do it. We are working on it in these type of graphs. Yeah, work is going on that direction.
But something looks or it's random, or what exactly? Have you observed something still now, or and then trying to prove it, or it's still an open problem and things like that?
Yeah, it is like a corona kind of thing. It is coming in most of the cases, but we are unable to get the general result. But that observation is there. It's kind of every time we are getting corona kind of graphs.
So now I would like Professor Kalita to say whatever he wants to say about this conference or about anyone and anything like that. Please, Kalita.
Yeah, I must thank the organizer for giving me the opportunity to talk here in this 100-year celebration of Professor C.R. Rao. Thank you very much.
All right, so to end this session, I would like to thank both the speakers, Professor Sivakumar and Professor Debajit Kalita. At the same time, I would like to thank Professor Manjunath, who invited me to chair this session. Thanks a lot, Manjunath, and thanks everyone else. Thank you.